Okay, so let's continue for our discussion about lossy transmission line. Um, well, the most prominent change in terms of lossy transmission line is the introduction of the attenuation constant alpha, which is combined with the phase constant beta to form the so-called propagation constant gamma. So as you can see from 7.66, the propagation constant is the sum of the attenuation constant alpha and the phase constant J beta. The alpha and beta value can be found with transmission line parameters. That is the RLGC model to per unit length, resistance, inductance, conductance, and capacitance of the transmission line. So as you can see here, they are formed as the square root of the product of the series components R plus J omega L times the shunt components G plus J omega C. So they can be found as for the corresponding attenuation constant and phase constant. Another important parameter for characterizing the transmission line property is the characteristic impedance Z sub 0. And conventionally, for lossless transmission line, the characteristic impedance is a pure real number. Okay, it's a pure real number. If the attenuation of the transmission line is taken into account, the characteristic impedance is not necessarily a real number. As you can see here, according to the R and G values, it can be a complex number. So what is the significance of characteristic impedance of a complex number? It suggests the voltage and currents on the transmission line is not only different as a magnitude ratio. The characteristic impedance is essentially the ratio of voltage magnitude over current magnitude. However, if it is a complex number which can be expressed in terms of magnitude and phase, then it suggests there is a phase difference between the voltage signal and current signal on the transmission line. So that may be something we need to consider about. And to the left are the transmission line equation for voltage signal and current signal. So we have seen the transmission line equation many times. So the only difference comparing to lossless line is the minus J beta Z term is replaced with minus gamma Z term. The phase constant term is replaced with the propagation constant terms, which means the exponential term can be separated into a real number, that is exponential minus alpha Z, and a phase representation of exponential minus J beta Z. So for lossless line, the magnitudes on the transmission line remains the same, while in lossy transmission line, the voltage and current magnitude will become smaller and smaller due to the presence of attenuation, due to the presence of loss. So in this part, we would like to examine the effects of alpha, the lossy part of the transmission line, on the transmission line equation, on the propagation constant, on the characteristic impedance, to see happens if a small alpha is taken into account. Now that the alpha can be regarded as small number because we are referring to the low loss transmission line. Okay, if alpha is a large number, of course, signal will die out quickly on the transmission line. All right, so in the previous slide, we have seen the relationship between alpha, beta, the attenuation and phase constant with respect to the per unit length properties. And here is some reminder about the properties of the RLGC model. They cannot be regarded as constant number. They are actually function of frequencies, which means the inductance, the capacitance, the resistance, and conductance may vary as the frequency change. But fortunately, in actual practice, usually the RLGC value can be regarded as constant for a specific band. 也就是说，在我们一般在做微波电路的设计的时候，即便说学理上来讲 ，RLGC 它都是随频率而变化的，但它的变化量其实没有那么大。所以，假如我们在做传输线的电路设计的时候，你有兴趣的频段，可能比如说10到20 GHz， 或者说毫米波频段可能26到29 GHz。只要你的频段不是跨越的很大的话，那其实大部分的情况底下，这个 RLGC 可以被视为是定值，视为是定值。当然，只要你的频率变动的幅度比较大，比如说可能是几百 MHz 的 VHF 频段，然后跳到38 GHz 的毫米波频段，那个频率差100倍，那它所对应到的 RLGC value 可能就有所变化了，那另外一个重点就是说，这个所谓的 RLGC value 怎么来的？要怎么样知道？用做实验的方式，一般来讲，所以基本上你假如说，你要去有一个新的那个 substrate 的一个板材要测试的话，基本上我们会在上面画一些像微带线这样的基础的传输线形式，然后去量它的一些特性，量它的相位变动。根据量到的相位变动来去反推，这一个材质或这个传输线形式它所对应的 RLGC value，一般来讲用做实验的方法来去得失，那个实验不会很困难啦，因为这些相对的实验设计不是太困难的事情 ，OK，so usually we will using experiment method to determine the value for your interested band, So now let's take a closer look about the propagation constant expression for a low loss transmission line. So here we can this derivation are based on the assumption that the lossy part R, the resistance R, and the conductance G are small numbers. So therefore, we can do the following approximation based on the based on the fact that omega L, the omega L is much greater than R, and omega C is much larger than G. So we know the expression for the propagation constant gamma is the square root of the product of R plus J omega L times G plus J omega C. If you taking the J omega L part and J omega C part out of the small brackets, you have this 1 plus R over J omega L and 1 plus G over J omega C. And now the product of the two terms in small parentheses will end up in 4 terms, right? But we know the fact that omega L is much greater than R and omega C is much greater than G. So R over J omega L is a small number. It's a number much smaller than 1 and maybe close to 0. Okay? Now, and so does the second term, G over J omega C. In fact, you should have the fourth term, which is the product of R over J omega L and G over J omega C. However, because this is the product of two small number, so it will becomes an even smaller number. So that's the reason why we drop the fourth term. We only keep three terms in this square root sign over here. So that's the reason why the equal mark over here is replaced with an approximate mark. Okay? So we already used the approximation that the product of two small terms is much smaller than the other terms. So here we only have three terms. Okay? And next, we will use another approximation so that we can drop the square root operator over here. We use the fact that if you have a number as 1 can be expressed as the 1 plus x to the nth order, to the nth order product, then if x is close to 0, if x is much smaller than 1, is very close to 0, then this thing can be approximated as 1 plus n times x. So if you take a look at this part here and using this approximate relationship, then we can say that n over here is 1/2. The square root operator is 1/2. N equals to 1/2 here. And the x part is the sum of the last two terms. So you can drop the square operator over here as 1 over 2 times up over J omega L plus G over J omega C. Okay, so again, we will use the tilde sign here to show this approximate relationship. Okay, the next thing, here we see here is a J omega term, and here are J omega term and J omega term here. So we have three terms. Basically, we have three terms. But the first term is imaginary, but the second term and the third terms can be real number. So in this operation, we try to separate real part from imaginary part. So the real part will be combined with this. You have J omega cancel with J omega over here. So the first part, the real part, is 1/2 times R times the square root of C over L plus G times the square root of L over C. So this is the real part, which can be related to what? Related to the attenuation constant of gamma, of the propagation constant. So here, with the assumption that R and G are small, you have a low loss transmission line. Then alpha can be derived like this. According to your circuit model, according to your per unit length resistance, capacitance, inductance, and conductance, you can derive the attenuation constant alpha. The next thing is to examine the imaginary part. So in this equation, the imaginary part is J omega times the square root of L times C, which is actually the same as the beta in lossless transmission line. So the beta expression is essentially the same as the lossless transmission line, which is not too surprising because we conduct this derivation based on the fact that alpha is small. So it has limited perturbation toward the other parameters. So the phase constant beta expression, well, is about the same as before. So it's still expressed as omega times square root of L times C. Next is the velocity of propagation. Velocity of propagation, which by definition is omega over beta. Omega over beta. And using the result above, the velocity of phase, velocity of propagation, is 1 over square root of L times C, which has no which has nothing to do with R and G, with the low C per meters. So, well, which means for low loss transmission line, except for the attenuation constant, the other parameters are about the same as lossless transmission line. Okay? So here we have the velocity of propagation and the phase constant are the same as lossless transmission line. So the next term is to determine the characteristic impedance Z sub 0. We know that if R and G are non-zero, which means you have a low C factor in your transmission line, the Z sub 0, the characteristic impedance can be a complex number. It can be a complex number. However, let's do the derivation in the following to check under the condition of low loss. So originally, the characteristic impedance is expressed as the square root of R plus J omega L divided by G plus J omega C. So we're taking the J omega L out and J omega C out, so here is 1 plus R over J omega L, and the denominator is 1 plus G over J omega C. And this terms can be taken out as square root of L over C, as we have it before, for lossless transmission line. Then the division over here can be regarded as 1 plus R over J omega L and 1 minus G over J omega L. Did you notice that we secretly use this relationship? 有没有？这边你有没有看到？刚刚那个推导其实已经有趋近了哈。这边本来是等号的，这边变成是2个破折号，表示趋近的意思。因为在这边的分母，本来你应该把它写作成是1加 G over J omega L J 加 G over J omega C 的负1次方，对不对？但你用这一个 small number 的 approximation， 所以那个负1次方就被甩到前面来，然后后面就变成是 G over J omega C 所以把它用这一个减号来把它取它的分母的这一项，把它取趋近之后，它就变成是跟分子乘在一起那你这边要多一个负号，变成相减。那这边本来应该两相乘，应该有4项，对不对？但我们知道后面那个是小数字，所以小数字乘小数字变成更小的数字，就可以直接把它踢掉了。所以在这一步里头呢，你只有3项，并没有4项So the first 3 terms, 1 plus R over J omega L minus G over J omega C is here, and then we will use this relationship again. 1 plus x to the x n time equals to 1 plus nx. So here n is what? 1 over 2. And the last 2 terms are combined together. So this thing can be approximated as 1 plus 1 over 2 times R over J omega L minus G over J omega C. So for the characteristic impedance, you see, this is a real number. This is an imaginary because you have a J in the denominator, right? But at high frequency, which means omega is a large number, and for low loss case, which means R is much smaller than J omega L, and G is much smaller than J omega C, the significance of the last two terms are not that important. So we drop it directly. We drop it because it's a small number. So the approximate value for the characteristic impedance of a low loss transmission line is still L over C and taking the square root, which is the same as the lossless transmission line. Well, then this shall make our life easier. Okay, so you don't have to dealing with very small imaginary number due to the presence of attenuation, things like that. So for the low loss line, the expression for beta z sub 0 are essentially the same as loss for a lossless line. So for low loss lines, the only thing that you need to consider is alpha. This is not negligible. All the other things are about the same as lossless transmission line. All right? So for low loss condition and omega L, which means omega L is much greater than R and omega C is much larger than G, so this condition can be made at very high frequency or very small value of R and G, which means your attenuation, real attenuation factors are small at lower frequencies. So as already pointed out, for the general case, conventional, it's more convenient to determine experimentally the value of Z sub 0, the characteristic impedance, and the propagation constant gamma, than it is to compute them analytically. Analytically 这个字是什么意思？这一集什么意思？就是用算式去分析出来的嘛，所以说阿尔法值跟 Z 值啦，或者是你对应的 RLGC 值，基本上在实物上都是用实验去量测的，比较容易得到了，比你去那边推那个形状或进行全波模拟来去算来的快速又准确了So the experimental technique is based on the measurements of the input impedance of the line for two values of load impedance. 所以我们会在传输线上面接上不同的负载，然后去进行输入阻抗的量测，而这些输入阻抗反射系数的量测结果就可以帮助我们去计算所要的这一个传输线的参数To obtain the expression for the input impedance, we first write the general solution for the phasor line voltage and current given by equation 7.68 and 69, respectively. In terms of the distance variable D measured from the load toward the generator as opposed to Z measured from generator to load. So here we have we need to change our expression, our transmission line equation a little bit. So in this page, you see the voltage and currents are written as function of Z, which is the distance counting from the left-hand side, counting from the generator side. And Z can be a large number in the right. 所以这边的话是我们之前所推导的传输线是以 Z 的观点 ，Z 是从左到右计算传输线上面距离 generator 的位置。这个描述是用 G， 但我们这里头要把它换成 D， 这是另外一个描述。而 D 的描述是从哪边算起？从右边的负载算起，所以 D， if the observation point is close to the load, then the corresponding D is a small number. On the other hand, if you are looking from the generator side, then you will have a large D number. So with the replacement of D toward so we use minus D to replace Z 所以原先的传输线关系式是用 Z 的观点，从左边开始算过去的观点来写的。但这里我们用 D 的观点，也就是距离负载端的距离所以把原来的传输线关系式里头的 Z 的 Z 换成是负 D， 所以本来第一项是 exponential minus gamma Z is replaced as exponential gamma D. And for the second term, it's originally labeled as exponential gamma Z. Now it's replaced with minus gamma D. And you can do the same for the current signal. So in 7.72a and b, you have transmission line equation expressed in terms of the distance toward the load, which is marked as D. And here is an alternative expression for VD and ID functions. So to the right is try to replacing the V minus per meter with gamma D, the reflection coefficient view from the position D. Because if you taken the V plus sign out, then the second term will be lead by V minus over V plus, which is the definition for reflection coefficient gamma. Gamma is defined in terms of the reverse going wave V minus over the forward going wave V plus. So we can change the expression for 7.72 as the ones shown here, 7.73. So the voltage signal is V plus exponential gamma D times 1 plus gamma D. And for the current part is V plus over Z sub 0 times exponential gamma D times 1 minus gamma D. Okay, and down below is the definition for reflection coefficient at a position D. Note that it can be translated by the reflection coefficient at the determination, which is gamma R, which is the ratio of V minus over V plus. Now, with the reference point moved to position D, then you need to add a phase correction term over here. That shall be the round trip distance from the observation point D toward the load position, which means D equal to 0. So the phase delay accumulated with this observation point change shall be exponential minus 2 times gamma D. And note that we are talking about low C transmission line. So exponential minus 2 gamma D can be further decomposed into a real part. And the imaginary part, well, it should be referred as the attenuation part. The first term is the attenuation part, which is expressed as exponential minus 2 times alpha D. And the second term shall address the phase change when moving in the transmission line. So it is exponential minus J times 2 beta D. Okay, so here we attempt to expressing the transmission line equation and reflection coefficient expression in terms of D and alpha, the attenuation constant. So equation 7.74 is the voltage reflection coefficient at any value of d, and gamma r is the voltage reflection coefficient at the load. 所以这些式子还蛮重要的哈，请你要记得看过，要对它有印象，好吗？好，那我们继续。So here is the expression for reflection coefficient at the position D. However, we shall be more interested about the input impedance at the position D. So in the previous slide, we have gamma D equals to gamma R times exponential minus 2 times gamma D. Now we can calculate the input impedance at a position D, which is expressed as the ratio of voltage at D over the currents, total currents at D. And the V over I, voltage over current ratio, for the characteristic admittance expression, can be replaced with Z sub 0 times what? Times 1 plus gamma D over 1 minus gamma D. Yeah. Because using the what? Using the total voltage over total current, which can be expressed in terms of V plus and V minus and gamma R. So by substituting the V over I ratio with 1 plus gamma D over 1 minus gamma R, we can have the expression for the input impedance at a specific position. Now, the parameter that we are interested in is the input impedance of a line of length L, and which is determined by the load impedance Z sub R. 所以下半部的话呢，我们试着要写出特定长度的传输线 L 长度的传输线，它的输入阻抗。而这个输入阻抗会跟谁有关？会跟你的传输线长度有关，会跟你在传输线右侧它的反射系数伽马 R 是有关的哈。这里头哈，我要提醒各位的一件事情是搞清楚，因为我自己在备课也都会搞混哈。V plus V minus VD ID gamma D ZD 还有啥？还有伽马 R， 还有大概这几个吧。这几个差别在哪里？你自己跟着我看一下哦。V 正是什么 ？V plus 是什么？在传输线上面往右边跑的讯号，在左边还是右边？右边哈，在 R 那个地方哦。其实这两个都指的在 R， 都在传输线的那个这边了哈，或者 D 等于0的地方了哈，都在 D， 这两个其实都在 D 等于0的地方。伽马 R 也是哦，所以伽马 R 是直接在负载端所看到的反射系数，这两个呢？这两个就是你传输线上某一个指定位置假如你指定这个地方是 D 的话，这边看到的 total voltage、total current，所以注意一下。这两个有没有一样？但基本全工人搜寻很简单哦。 不一样啊，它是这个加这个哦，哦哦，它是往正的跟往负的加在一起啊，OK 啊，所以这个也是一样啊，这个是什么？我们刚刚不是还有传输线关系是吗？啊，这个 VD 是什么？V 正 exponential gamma d 加上 V 负 exponential minus gamma d 啊，所以它一样是有正的 part 跟负的 part 啊。然后这个 exponential gamma d 是干嘛？调相位用的啊，调传输的相位用的啊。所以这两周不是同款的概念哦啊。OK， 在 VD 跟 ID 是 total voltage、total current。然后所谓的 total voltage 表示里头有 forward going voltage， 还有 reverse going voltage，forward going currents，reverse going current。好啊，当然位置上就没问题了，它这边小括弧都有 D 嘛，所以是在这边看到的。那这边看到的会有伽马 D， 但伽马 D 透过一定的转换之后，就可以让你得到 ZD。啊，在这个地方看到的 D， 而这个 ZD by definition 是什么 ？VD over ID 嘛，对不对？好，好，所以看那个 slide 的时候，看课文的时候，看 slide 的时候，稍微要搞清楚哦，哈，因为有一堆嘛，对不对？啊，所以搞不清楚的时候，你就容易混掉，啊 ，OK。我小时候大学念书的时候也常常搞混，哈，也是一堆人没注意到，哈。好，所以这边请你特别留心啊。所以你看7.74就看得出来嘛，哈。So equation 7.74 shows the expression for the reflection coefficient at the position D, which by definition is the voltage ratio of reverse going voltage over forward going voltage. So they are labeled as V minus D and V plus D, which means they can be translated from reverse going voltage at the load and reverse forward going voltage at the load. So you see, you need to figure out the relationship of this and this term. So they are the same. They are exactly the same. The reverse going voltage at the position D can be expressed as the product of the reverse going voltage at the load times a phase adjustment. Oh, well, I'm sorry. This is not only the adjustment in phase. Exponential minus gamma D can be further decomposed into exponential minus alpha D times exponential minus J beta D. Okay? So it compresses the adjustment in magnitude and the adjustment in phase. Gamma D comprise both adjustment in phase and magnitude. So that's the reason why I would like to label a mark over here. So overall speaking, gamma D can be expressed as the product of gamma R, that is the reflection coefficient at the low position, times the round trip adjustment for magnitude and phase, which can be further decomposed into attenuation term and phase variation term. All right? 好，这要看好清楚哦。All right, so with the low loss transmission line condition, the line impedance ZD, of course, can be expressed as the ratio of total voltage at D over total current at D, and they can be expressed as Z sub 0, the characteristic impedance of the transmission line, times 1 plus gamma at D and 1 minus gamma at D. And gamma at D can be decomposed into, using this relationship, as gamma R times exponential minus 2 times gamma D. Okay, so you can substitute this relationship into this expression. And this thing can be further decomposed. So you should do that at home. Okay, be sure to do that at home to check out the relationship. Because here, gamma r is further decomposed into, using the definition of gamma r, that is zr minus z0, z sub 0 divided by zr plus z sub 0. And you do the same for the one in the denominator. And if you times the numerator and denominator both with zr plus z sub 0, that is, you end up with this term. And the first term is simply the sum of z sub r and z sub 0. The second term is z sub r minus z sub 0 times the exponential minus 2 times gamma L. Well, you can pick up one exponential minus gamma r in the front, so that it can be expressed with exponential plus gamma L times exponential, here is exponential minus gamma L. 后来我忘记看，分子分母都提一个 exponential gamma r 出 L gamma L minus gamma L 出来，拿到外面，好，拿出来那个没有用，那个没差嘛，因为相除还是等于1，啊，但是你这样的话，你就变成前面这一项是乘上 exponential 正的 gamma L， 后面那一项就变 exponential 负的 gamma L， 然后你再两配对，啊，两配对，用 hypersine 跟 hypercosine 的定义去做两配对，那这个是可以做得到的啦，哈 ，OK， 但你回去，我是建议你回去要自己做一下，会对它有印象。所以你会出来的是右边最后右边那个结果，哈 ，zr 变成是 zr 乘上 hypercosine gamma L 加上 z0 乘上 hypersine gamma L， 那分母的部分又有一点点交换，哈，变 zr 的 hypersine gamma L 加上 z0 的 hypercosine gamma L。好，换到这边。换到这边大概就是换到这边的目的是什么？这个是最左边的输入阻抗，而这边呢是传输线本身的特性阻抗已知，传输线的负载的阻抗可能已知，然后还有传输线的传播常数伽马，还有传输线长度 L， 啊，所以。用这边等于是说，你把一些传输线的基础描述的参数套进去，你可以得到你这一支传输线在特定位置、特定距离的输入阻抗啊，输入阻抗。那，这边还在做进一步的转化哈，这边是把上下都除上 hypercosine gamma L。所以上下都除上 hypercosine gamma L， 所以这两个是相同的哦，这两个是相同的啊。所以上下都除上 hypercosine gamma L 就变成是这边是1，这边是 hypertangent gamma L 哦，然后这边是 hypertangent gamma L over 1，所以这两个是一样的。但意思是什么？这边你要按4次的计算机，这边只要按2次哦。OK 啊，所以一样的啦啊，一样的东西。然后。来，我把这2页讲完。Okay, let me finish. Okay, for lossy transmission line, if you have a lossless transmission line, the power went into the transmission line will go into the load, PR, with some energy stored in the transmission line. If you have non-matching condition, if you have standing wave. But in a time average sense, once you have charged the transmission line, then all the other power delivered by the generator, provided by the generator, will be delivered into the load. 我再讲一次哈，一般无耗损的传输线，传输线上面会不会有能量？会，但是那个能量是存在上面的，不会被消耗掉。所以一旦你的传输线系统进入到稳态，你的 generator 端所提供的能量，最后都会由谁消耗？由负载消耗。所以这边假如提供1瓦，那最后在这边会消耗掉1瓦。可是真实的状况当然没有无耗损传输线，真实的状况是你有一个有耗损的传输线，所以 PT 这边进来的能量，它最后会跑到哪里去？一部分变成 PR， 一部分变成在上面的 PD 啦 ，D stands for dissipation， 所以简单的能量平衡，你 transmitter 所提供的或 generator 提供的功率P， 它只有2个去处，要么提供给负载，要么耗损在传输线上，所以对于传输线系统的分析，一个很重要的就要知道这有多少，这里有多少嘛，所以这个题目重要 ，OK 好，提示也提示到这里了，OK， 你看考古题有嘛，对不对？好，所以我们先从简单的，等一下还有一个题目啦，我们大概看不7.8，大概明天才讲得完了所以我们先看一下相对的概念。这个是平均的那个功率嘛time average 的那个 power provided by the generator. So, it's 1/2 times the real power of VD times the complex conjugate of I at D. So that's the time average power passing through point D. Okay? And using the expression for total voltage and total current, it can be rewritten in this form. And due to the time limit, I will skip about the derivation over here. Let's check out the result. That will be 1/2 times the V plus 注意V plus 在哪里？右边右手边的右手边的那个顺向电压的平方乘上 Y0 complex conjugate， 这是啥 ？Z0 的导数而已啦。那取 complex conjugate 有没有意义？数学上有意义，但实务上没有。为什么？因为你只要是50欧姆的话 ，Y0 就是 0.02。low loss transmission line 的话，你的10步也就是，所以基本上，只要是 low loss transmission line， 这个地方等于0了啦。所以那个 Y0 基本上就是 G0 了啦。然后虽然这里头它把它写成2B0 那后面的话，后面那个这个中化5大概写成实数乘实数的就虚数乘虚数的就变10步相，虚数乘实数的就变成是虚步相但你会看到最外面有一个 real part 的 operator 所以后面这一项其实是不重要我们等一下会把它，对不起讲错了，这边两者相乘的时候这个的虚步乘上后面那个虚步会变实数，但是因为那个 B0 在 low loss transmission line 是相当于等于0的，所以事实上式子没有那么复杂。后面这一项我们不会看所以虽然式子看起来有点多像这个 7.82， 但是真正我们在计算的时候会用到只有前面这几项，1/2 V 正平方要，这个就重要了根据你的传输线的那个长短， 乘上它的 attenuation constant， 然后这个 G0其实就是 Y0， 也就是 Z0的导数。这个是你在那个左侧所看到的反射系数，这也是可以算得出来的。后边这一路边去插笔啊。好，那我们明天再来讲 example 7.8这一个例题。好，那明天我们剩一些东西了，所以我在猜，我明天大概1节课就可以，我会再拿一些以前的题目的类似题来讲了哈。不过大概明天大概差不多就1节课的量哈。